Hey, welcome back to Calculus. In this video lecture, we're going to start our work in section 2.8 about the derivative as a function, not just looking at it at a single point, but as a function of the input variable that is the input variable of the original function. There's a lot of material in this section, so I'm going to cut this into two, maybe even three videos. We'll see how the second one goes. But here I've just selected some of the learning objectives that are on the Canvas page for this section. And in particular, in this video, what I want to try to do is get us to understand how we can think of the derivative as just some other function of x. And then mainly the purpose of this is to give you an idea of how to compute this derivative. You've already done these computations, but we'll just look at it, what it means if we're not specifying where we're taking the derivative. And then we'll end by talking about two different notation schemes that come from kind of two of the founders of our modern calculus, Isaac Newton and Gottfried Leibniz. And I'll try to give you a little hint as to why both of these notation schemes are around. No one of them has gobbled up the other one. All right, so let's just get going. I'm going to write this as we go in this one. And so let's see. We know what the derivative is. It's a limit of difference quotients, and we've been computing it at different values of a. So the main idea of the whole section here is that if we don't specify a certain value of a, so if we have some function f that's defined on some domain, then we can compute its derivative at any value of x. Yeah, so we don't have to pick a specific value, compute the derivative, and then pick a specific value, compute the derivative. We can just compute that derivative in terms of the original input variable x itself. So if I just write f prime of x and then I use the difference quotient definition, I'm going to write, well, it's the limit as the change goes to 0, h goes to 0, of f of, I'll just put x plus h, so leaving it as a variable, minus f of x, and divide by h. And when we're all done, this will be an expression that's also still has x's in it. It's also a function of x. And then you can just plug values of a into that expression if you want to compute those derivatives. So thinking of it like this, thinking of it as the derivative is f prime is a function of the same variable that f is. All right, let's do some computations. Some of these are going to feel a little bit repetitious, but I like to start with something that's algebraically kind of easy on the eye. So let's say we take a function like x squared. All right, I want to compute the derivative of x squared as a function of x. So using that definition that we just wrote above, f prime of x is going to be the limit. In fact, you know what I might do? Because I'm going to be writing this so many times in this lecture, let me just copy that thing, and then I don't have to keep writing it over and over and over again. So there you go. Every one of these computations is going to start like that. And then I can put in the details of what this f is. So it's the limit as h goes to 0. In this case, f is x squared, so it's x plus h squared minus x squared all over h. Okay, so that's the limit as h goes to 0 of x squared plus 2xh plus h squared, just expanding that binomial over h. X squared and its opposite cancel in the numerator, and the remaining terms are divisible by h. So we've been doing a lot of computations like this. If it feels new, it's because I don't have a numerical value for a in there. I'm leaving it in terms of x. So my answer will be in terms of x. Cancel those h's. So we've got the limit as h goes to 0 of 2x plus h, and now we can take that limit by direct substitution and we get 2x. All right, so as advertised, the answer now is not a number, but it's also a function of x. So let me just summarize that if f of x is equal to x squared, the squaring function, then its derivative, f prime, is 2 times x. So in particular, if you wanted to compute the derivative at some value of x equal to a, you don't have to recapitulate this computation over and over and over again. You can just plug a into the derivative. So I think I remember in a previous lecture, we computed f prime of 4 by the limit definition. All right. Well, f prime of 4, we can do it here. Or sorry, maybe it was f prime of 2. f prime of 2, if I want to stick with a previous lecture. F prime of 2, well, we should just take that 2 and multiply it in here, and 2 times 2 is 4. And that's maybe what you recall when we computed f prime of 2 directly in the section 2.7 lecture. We got 4. Well, now I can just plug 4 into this formula. I've got one expression that gives me the derivative at any place. Yeah. So if you want to know what's the slope of the tangent line when x is 10, well, it's 20. What's the slope of the tangent line to x squared when x is minus 5? What's minus 10? In the next video lecture I'm going to make, we'll talk about how you can think about these tangent slopes and the shapes of the graph. We're going to talk about this a lot, in fact, in chapter 3. But to keep this video short, I'm going to try to resist the temptation to spinning off into these tangents and just repeat these calculations. So this is the first one. What's the derivative of x squared? It's 2x. All right, let's do something else. How about we take, I'll change the names of the functions. How about if I take the function g of x to be, say, just a constant like 7? What do you think the derivative of a constant function is? What's the slope of a tangent line to a graph that's a constant function? If we drew a quick sketch of this graph over here and an xy plane, its y values are 7 no matter what its x value. So what's the slope of the tangent line to that line? It looks like it's always going to have slope 0. So I kind of have this guess, yeah? I'm going to guess that the derivative g prime of x is equal to 0. And I don't think it's special that my constant was equal to 7. I think it could be any constant. But let's use this definition to see it. So g prime of x, it's the limit as h goes to 0 of g of x plus h minus g of x over h. Okay, in this case, g is a constant function. So this is the limit as h goes to 0 of 7. G of x plus h is 7. So is g of x. Okay, that's the limit as h goes to 0 of 0 over h. That's 0. Good. So if g of x is equal to 7, any constant, its derivative is 0. The derivative of a constant function is 0. I'm going to write that more generally. If g of x is equal to any constant, its derivative is 0. Cool. Let's do another one. Let's see. How about something like this? How about we take h of x to be the square root of x? I want to compute h prime by the definition. So h prime is the limit as h goes to 0. This is the template part of h of x plus h minus h of x all over h. Limit definition of the derivative. So that's the limit as h goes to 0. In this case, square root of x plus h minus the square root of x all over h. And how do we handle limits that have differences of square roots in them? Multiply by the conjugate. So I'm going to multiply by x plus h plus x, square roots everywhere. Sorry, it's hard to speak and write at the same time when you're not talking to anybody. And so I'm going to multiply by that conjugate expression over itself, and then algebraically simplify that thing. So what do we got? When you multiply out in the numerator, you're going to get x plus h. Cross terms cancel, minus x. Bottom, I'm not going to try to do anything. I just have to make sure I don't drop any of the terms. All right, x minus x is 0. So what do we get? Limit as h goes to 0 of h over h times that quantity. Now h over h is 1, so those cancel. In this final expression that I'm writing, I can directly substitute h equals 0 without dividing by 0. And when I do, I get 1 over the square root of x plus the square root of x. So that's 1 over 2 times the square root of x. All right, so to summarize, if h of x is equal to the square root function, its derivative, h prime of x, is 1 over 2 times the square root function. Nice. So now, if you wanted to pick a specific value of x in the domain of h, you don't have to recapitulate that limit computation every time you want to know the derivative. Like, for example, if somebody asked you, like, hey, what's the slope of the tangent line? Sorry, my handwriting's messy, but I don't want to make this video last forever while I try to print neatly. What's the slope of the tangent line to the graph of h of x at the point, I don't know, 36, 6. Square root of 36 is 6. Back in section 2.7, we would have started to answer that question by taking a limit, right? We would have gone back and said, oh, you want to know h prime of 6. Well, we've got a formula for h prime. It's valid for any value of x in the domain of h. So we don't have to recapitulate that every time. H prime of 36 is 1 over 2 times the square root of 36. That's 1 over 2 times 6. That's 12. Okay, so that's kind of the benefit of having this derivative as a function. You do the work for that limit once, and then you have it in your pocket forever. Okay, let's end with one more. I think I want to do one more. Maybe we could up the algebra a little bit here. All right. So let's try to do something where we're going to kind of flex our algebraic muscles a little bit here. Let's take a function. Let me just go back to f, recycling f of x. And why don't we try something like this? How about x, I don't know, minus 1 over x plus 1. This will probably keep us honest. Let's try to find f prime of x. Later on in chapter 3, I'll show you much more efficient ways to do this. So part of the purpose of this example is to motivate you to stick around to chapter 3. But here I want to find the limit of the difference quotient. Okay, so I'm going to take f prime of x, and it's that limit. Do I still have it in my clipboard? No, I have to write it again. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, let's see if we can't start handling this thing. Whenever I have fractions of fractions, I don't really like to have that multiple division sign. So I'm going to switch, instead of this dividing by h, I'm going to be writing it as multiplying by the reciprocal. All right, so that's the equivalent of dividing by h. So now I don't have to think about fractions of fractions. So what is f of x plus h? Okay, everywhere I see the input placeholder x in f, I have to replace it with x plus h. So that's going to be x plus h minus 1 over x plus h plus 1, right? And then I have to subtract f of x. So what's f of x? Well, it's x minus 1 over x plus 1. Now we need to get a common denominator. We need to get a common denominator because we need to eventually cancel this factor of h so we can directly substitute h equals 0. So the common denominator I'm going to take is just going to be the product of those two denominators, which basically means I have to multiply the numerator of the fraction on the left by the denominator of the fraction on the right, and vice versa. All right, so we'll do the algebra slow here, but we got x plus h minus 1 times the quantity x plus 1. And then we're subtracting x minus 1 times the quantity x plus h plus 1. That's going to be our numerator, and our denominator is going to be the product of those two things. All right, so now I still can't see how the h cancels. We have to basically do a bunch of algebra up here until we can see how that h is going to cancel. So I have to distribute out some terms here. I'm not going to touch this denominator with a 10-foot pole. It's not going to help me cancel this h. That's my end goal. So I'm just going to keep copying it. So let's see what we got. We've got the limit as h goes to 0. Notice, maybe I'll try to say something helpful. Notice how I'm willing to write many, many lines with small steps to avoid algebra errors. I think that's good advice in general. And now I'm just going to distribute. I'm going to be multiplying this x by all three of those terms, and when I'm done, I'll multiply by the 1 by all three of those terms. So in the numerator, we're going to get x squared plus xh minus x, and then multiplying everything by 1 will give x plus h minus 1. Over here, I want to be careful. It's a minus sign, so I'm going to put a parenthesis there and do the same thing. X squared plus xh plus x minus h minus 1. Can you still see all that? That's all over x plus h plus 1 times x plus 1. Getting a pretty good hand cramp going here, but hopefully you can still see what I'm writing. Okay, I'm willing to simplify this thing slowly. I hope this video isn't getting too long. You can skip ahead. If these computations are routine to you, then skip ahead. There's no need to watch me do all this algebra, but maybe it's helpful for some of us. So I'm going to write those terms. I'm just copying, and now I'm just carefully moving through my minus sign. So minus x squared minus xh minus x plus h plus 1. That's all over this product, x plus h plus 1 over x plus 1. And now let's go red pen and do some canceling here. I see an x squared and a minus x squared. They're gone. I see an xh and a minus xh. I see minus x and x, minus x and x. I see minus 1 and 1. It is a miracle. Everything cancels there except for two h's. Two h's survived the cancellation in the numerator. So when you do all that, what do you get? 2h upstairs, x plus h plus 1, x plus 1. Cancel h over itself, that's equal to 1. And we get the limit as h goes to 0 of 2 over x plus h plus 1. We just canceled the reason we couldn't directly substitute, so now we directly substitute h equals 0 into this limit. So we get 2 over x plus 1 times x plus 1. Or if you want to write that, it's 2 over x plus 1 squared. All right? So I have to scroll back to remember what h of x was. It was a while ago, x minus 1 over x plus 1. I'm just going to summarize. If h is equal to the function x plus 1 minus 1 over x plus 1, then its derivative is 2 over x plus 1 squared. All right, and then we could use that derivative to answer questions about tangent slopes at any point in the domain of h. All right, so next time in part 2 of this section 2.8 video, we're going to talk a little bit more about the qualitative analysis. You know, what can we say about this derivative? What kind of information does it give us about the function? But this was 1, 2, 3, 4, 5 examples showing you what the mechanics of computing a derivative by taking limits of difference quotients is. All right, thanks for listening.